All right, so moving back to Mercury, because Mercury is very close to the sun, and remember Mercury has an 88-day year. Question? What? Okay. Well, there may have been a bunch of different objects formed, and some of them probably weren't in the same orbit. The thing about this, if you look at a simulation like this, it's sort of arguable that there's kind of a sweet spot there where you may be able to form multiple blobs that neither fall back onto the Earth nor escape completely. All right. So if you're going to form multiple blobs, simulations suggest they're actually going to be in pretty similar orbits, because if they're radically different, then they're either going to land back on the Earth or they're going to escape completely. So that kind of works out okay. I don't think, as far as I know, nobody's done a detailed simulation that backs up the two-moon idea yet. But it seems that it may be plausible, and it does explain some of the other observations that we do have, like the thicker highlands and lack of Marriott. But I wouldn't say it's conventional wisdom. It's not completely accepted. This was just an idea from last year, but I would say it's an intriguing possibility, you know. But one of the neat things about it is it shows you we don't understand everything you might think we already understand. Because it's our own moon we're talking about. We don't understand that process very well. But that's a good question. All right, let me go back to the model there. All right, so we know at the distance that Mercury is from the sun, and how its year is 88 of our days long. Right? So that's about, less than a quarter of the length of our year. So Mercury, being as close to the sun as it is subject to an enormous tidal effect from the sun, because the sun is, a million times more massive than the Earth. So what you've got is an enormous tidal effect acting on Mercury. So if Mercury were to try to rotate with respect to the sun, if Mercury were to suppose the clock is the sun and Mercury is spinning, well, then you're going to have a bulge pointed at the sun and a bulge pointed away. But there's no water on Mercury, so we're talking about bulges in the rock, just like with the ancient moon. So if Mercury tried to spin, different parts of Mercury would be expanding and contracting, and what would happen is the spin energy would actually be converted into heat, just as what we've seen has happened already to the moon. Now, the moon is in a tidally locked orbit around the Earth because of that process. So the expectation was that Mercury would be in a tidally locked orbit too. And observations based on one of my favorite Italian astronomers, Giovanni Schiaparelli, confirmed that Mercury is in a synchronous orbit, because he thought he saw features on Mercury, and he thought from those features that he saw on Mercury that Mercury actually was spinning every time it orbited, which would be a synchronous orbit, just like with the moon. But we now know, in fact, that Giovanni was perhaps partaking, this is really very cool on my part, but he may have been partaking of the vino a little bit more than was suitable at the time, because, and this is just a cheap shot. I don't really think Schiaparelli was drunk necessarily, but that happened in fun. But anyway, that was the conventional wisdom for around 100 years or so. But in 1965, we actually had the first capability to make a type of observation that would really tell us how fast Mercury is spinning. Now remember, I'm not talking about its orbit. We know its orbit's 88 days long. That's obvious, because you can actually see Mercury move through the sky. What we're talking about now is its daily spin rate. Whereas ours is 24 hours, what is the spin rate of Mercury? Well, if Schiaparelli had been right, then the spin rate of Mercury would be 88 of our days long, because it would be a tidally locked orbit, right? And you can't see, even to this day, you can't see the surface of Mercury from Earth well enough to directly see what its spin is. So instead, in 1965, we used the Doppler radar technique. And the idea here is we send out a signal of a known wavelength from a radio dish on Earth, and it bounces back off Mercury. Now remember how this Doppler broadening works. When the signal bounces back off Mercury, if Mercury is spinning, then the side of Mercury that's moving back towards the Earth is going to blue shift the bounced radio waves to have a smaller wavelength. The side of Mercury that's spinning away right here is going to be a receding surface, so that's going to bounce back waves which have been redshifted. It's pretty much the same thing we were talking about when we talked about rotation and broadening for a star. All right, so if Mercury were not spinning, if this weren't spinning at all, then the bounce back wave would just be the green wave. There wouldn't be any redshift or blueshift. But the faster you make Mercury spin, the stronger the redshift is and the stronger the blueshift is. So if you look at that, if you observe how broad the reflected radar signal is, the broader that curve is, it's going to be a bell-shaped curve, just like the broadening curve we talked about before. The broader it is, the faster the object is spinning. So when we actually do the analysis, what we find is that the sidereal rotation period of Mercury is 59 Earth days. So Schiaparelli wasn't too far off in the sense that it is rotating slowly, no question about that. But it's not rotating, well, it's actually, it's rotating a little faster than Schiaparelli thought, because he thought the day on Mercury was 88 of our days. In fact, it's actually 59 of our days. So Mercury's spinning a little bit faster, but it is spinning very, very slowly. And this number is just a very bizarre number because it's not equal to the length of the orbital time. So it's not tidally locked. So where the heck would a strange number like 59 actually come from? How could that, why would Mercury have that particular spin rate? Okay, so this diagram is again just looking at the reflected signal. Oh, by the way, this is actually the same idea as a police radar detector, because a police radar detector sends out a signal. It illuminates your car with a signal that has a definite known radio frequency, and then when that bounces back off your car, depending on whether you're going towards or away from the police officer, it creates a redshift or a blueshift. And if that redshift or blueshift is too big, you're speeding, basically, right? And so this is a very tiny difference that we're talking about. So the police detectors are actually based on special relativity, because special relativity is what dictates the redshift blueshift phenomenon. So you can use that to argue your way out of a ticket. Give the officer a quick quiz on special relativity. If they fail, say, I'm sorry, you don't have the authority to issue this ticket, and drive away. Just don't mention my name when you do that, please. All right, so back to the 59 days. An unexpected result, for sure. Schiaparelli was long gone at this point, so this is when the cool rumors about the drinking first emerged. But anyway, turns out the 59 days actually is a new type of spin-orbit relationship, a new kind of resonance condition that we haven't seen before. It's a little more complicated than what we've seen before, what we call a spin-orbit resonance. So we'll go through the details of that in a second, but let's just backtrack for a second and think about the simpler example of the moon for a minute again. So for the moon, it is a spin-orbit, we call it a spin-orbit resonance. We also call it tidal locking, because that's the name we use for this particular kind of spin-orbit resonance. But okay, so it's a spin-orbit resonance. It sounds kind of abstract, but all it is just looking at the spin period and the orbital period, and they're just equal to each other, the moon. They're just equal to each other. So the moon spins on its axis once every time it orbits, and consequently, those two periods are equal, so we call that a spin-orbit resonance of 1. And of course, because they're equal, the moon always shows the same face towards the Earth. All right, so let's now think about what's happening in the case of Mercury. For Mercury, it's a little bit more complicated. What we find is that the spin period, we just showed the spin period was 59 days, based on those Doppler observations of the spinning Mercury. 59 days. The orbital period is known to be 88 days. So they're not equal to each other. 59 is not equal to 88, right? So it's not tidal locking like the moon. But there is an integer relationship between the two periods. Turns out that 59 is 2/3 of the 88-day orbital period. The 59-day spin period is 2/3 of the 88-day orbital period. Okay, so on the face of it, this is still like, so what? I mean, okay, so we found an integer relationship, but this does not physically explain why we get these numbers, okay, or the relationship between them. So let's go and start looking at some pictures for the way the orbit is actually occurring in relation to the spin. So we're going to start here on day 0 at high noon. We have a stick here stuck on Mercury that's pointed to the sun. Okay, so we have a stick pointed at the sun at day 0, and then we've stopped Mercury, and now we let Mercury go again. And so what happens is, first of all, notice it is spinning counterclockwise, so that's another pattern that we've seen already for the Earth. The Earth spins counterclockwise as due to the North Celestial Pole, and so does Mercury. All right, so we have counterclockwise spin, and then what's going to happen is we're talking about the length of the sidereal day on Mercury. Now, remember there's a distant star out here, which the red stick is pointed at. It's pointed at the sun, but it's also pointing at a distant star. Now, if we wait for this orbit to occur and we allow the rotation to continue, 59 days after the starting point, the red stick is pointing to the left again. So that's one sidereal day because it's pointed at the same distant star for the first time since we started. Okay, so that's one sidereal day because it's pointed in the same direction. And remember, the distant star is miles away here. So these two these two stick arrows here, they're just pointing to the left. But this distant star is miles away, so they're basically still really pointing at the same distant star. So that's 59 days. All right, now if we go into the next year, okay, if we continue the motion, let's see, we started, so what we ended up with was day 74 here, and day 88. Okay, so day 88 is 1 year on Mercury since we started, right? Because the year is 88 days long. So, and you can see we completed one orbit. We started there, and now we're back there again. So this is 1 year later. But notice what's happened to the stick. It's not pointed at the sun, it's pointed in the opposite direction. So what's happened here, which is pretty bizarre, is that we've gone from noon to midnight on Mercury, at that one point on Mercury, in 1 year. Now I say it's noon because you see, we started at noon, right? The stick is pointed at the sun, so that's noon at that point on Mercury. This is midnight at the same point on Mercury. So in 1 full year, we've gone from noon to midnight at that point on Mercury. If we keep going, we're going to hit a new sidereal day over here. This is the second full sidereal day, because 2 times 59 is 118, so the second sidereal day occurs. Here's day 147. When we finally get back here, we finally get back to the way things were at the very beginning. 2 full years later, we've actually gone through 3 sidereal days, if we keep track of everything. And we've gone through just 1 solar day. So we have, it's a little bit confusing, but there's 3 different things that we're looking at here. We're looking at the length of the year. This is actually 2 full years that we've gone through, because we're at day 176. So we started at 0 time. After the first year, we have midnight, because the red stick is pointing to the right. After the second year, we're back to noon. So we've just gone from the original noon to a new noon, and it's taken 2 full years for that to happen. So 2 years on Mercury is equal to just 1 solar day. Incredibly, you know? 176 of our days is only going to amount to the time between 2 noons at one point on Mercury. But it's going to be 3 sidereal years because we saw the stick pointing to the left. We started with it pointing to the left, right? So that's the 0 starting point. Now here with 1 sidereal day, the next time it points to the left is here. That's 2 sidereal days. Then it keeps spinning and it points to the left again there. So that's 3 sidereal days. So in the period of 2 years, you have 3 sidereal days, but only 1 solar day. All right, so pretty bizarre. And I should say that although we've kind of teased this apart in a certain sense, we really haven't explained why it's this way. We're just, I would say we're still just kind of doing bookkeeping at this point. We're kind of figuring out how different times are related to other times, but we haven't explained why it's this way. Now something like this is not just going to be a coincidence because it would tend to decay over time. And yet we see this condition, 3 sidereal days for every 2 years.